In this video, we will learn the second fundamental theorem of calculus, and we will also learn its proof. The second fundamental theorem of calculus has another name. It's called differentiating integrals, because we will differentiate an integrals. That's why it's called differentiating integrals. Now, the statement of second fundamental theorem of calculus is, so the statement, suppose the function f, which is defined on the bounded interval ab and it goes to set of real numbers r, is continuous, then the conclusion is ddx of integration of a to x f of t dt equals to f of x for all x in AB. So this is the statement of second fundamental theorem of calculus. Now we will learn its proof. So to prove that, what we will do, we will define this part equals to f of x. Suppose this is f of x. So define f of x. So this means define integration of a to x f for all x in AB. Now what we will do, let x0 is a point on the open interval AB, then we need to show that so if this is f of x and if you take its derivative, then it will be f prime of x. So left side become f prime of x. Since we are considering a point x0 in that interval, so it is x0. So f prime of x0, and when x is x0, then right side becomes f of x0. So we need to show this one. Now what we will do, we will consider, let x is a point in AB with x is not x0, then f of x minus f of x0. By first fundamental theorem of calculus, it would be integration of x0 to x f when x more than x0, and if you flip this one, then it would be negative x to x0 of f when x less than x0. So for the function f, so this is A, this is B, and we consider 2 points. One is x0 and one x here. Now consider any point. Let c of x in x0 to x. So we consider a point c of x in this interval, c of x. Then by the mean value theorem, by the mean value theorem for integrals. So mean value theorem for integrals, we have f of x minus f of x0 over x minus x0 equals to f of c of x. Because by the mean value theorem for integrals, there is a point in that interval, so that in that point the function f should be integration of x0 to x f over x minus x0, and integration of x0 to x f is that one. That's why we wrote f of x minus f of x0. Now if we take limit on both sides, limit of x approaches x0, f of x minus f of x0 x minus x0, limit of x approaches x0 f of c of x. So we take limit on both sides. Now by the definition of derivative, the left side becomes, so by the definition of derivative, this part becomes, so left side becomes f prime of x0, and since the function f is continuous and x approaches x0, so the right side becomes f of x0. Since the function f of x is continuous at x0. So this is the proof. This completes the proof. Because here we also say this one. So this completes the proof. Thanks for watching.